Welcome back, critical thinkers. Today's TEK is G3B. Determine the image or pre-image of a given two-dimensional figure under a composition of rigid transformations, a composition of non-rigid transformations, and a composition of both, including dilations where the center can be any point in the plane. This video covers reflecting or flipping a figure. Our learning objective is to reflect or flip a figure in the coordinate plane. And you will know you have mastered this objective when you can be given a set of instructions on how to reflect a figure with a line of symmetry and then draw that figure. Every skill you learn in this video makes you a stronger problem solver. I know you can do this, so let's turn your practice into your superpower. Our first task is to understand just what is a reflection. So we have the official definition, and it states it is a transformation over a line called the line of reflection, or it's also called the line of symmetry, where each point of the pre-image and its image are the same distance from the line of reflection. No one will ever ask you this exact definition, but they will expect you to understand what it means to reflect a certain image, a figure, a point over a line of symmetry or a line of reflection, and you need to know how to do it. Now, just remember that a reflection is a congruence transformation. And what that means is the pre-image and the image are congruent. So these two triangles right here would be congruent because they are reflections. They're reflected over this line right here, which is the line of symmetry, but it's also known as the line of reflection. Now, the way we draw a reflection is we locate the vertices of the pre-image. So I have A, I have B, and I have C. What I do is I draw a perpendicular line from the vertex to the line of symmetry. So I'm going to do that for A, I'm going to do that for B, and I'm going to do that for C. Now, how do I know it's a perpendicular line? I'm going to measure this, and it should be equal to 90 degrees. This should be equal to 90 degrees. And this angle right here, it should also be equal to 90 degrees. So once I have this perpendicular line drawn from each of the vertices to the line of symmetry or the line of reflection, and I know that these are 90 degrees, and that is represented by the corner markers, what I do is I measure the distance from A to the line of symmetry. Then what I do is I take that exact same distance and I measure it from the line of symmetry out in another perpendicular line segment, or I just continue with this, the exact same distance. And at the end of that, I'm going to put my new point, the reflected point, and that is going to be here, M. Then note that this line segment right here and this line segment right here have to be congruent. They have to be the exact same length. So if I told you that this was 10 feet, you could look at me and say, this is also 10 feet. If I told you this was 6 feet, you would say, this has to be 6 feet as well. If I told you this was 15 feet, you would know that this measures how much? How much is this? Yeah, it would be 15 feet as well, because this segment and this segment are congruent. This segment and this segment are congruent. And this segment and this segment are congruent. And notice that these segments that we drew in are also perpendicular to that line of reflection or the line of symmetry. Once we have these points, so I've measured from the vertex to the line of symmetry, and then I use that same measurement and go out. This is my new point on the image. So I'm going to measure from C to the line of symmetry and use this exact same measurement to go out here, and O becomes my point on the image, my reflected C. And then I'm going to measure B, and I'm going to go out from the line of symmetry to here, and I measure it. I know that these two line segments are congruent. And at the end, I'm going to put my reflected point. So B and N are reflections of each other. So then what I do is I connect the points, and what I get is I get a mirror image of the pre-image. So if I folded this right here on the line of symmetry or the line of reflection, these two would match up perfectly on that piece of paper. Now we can say that triangle ABC right here is mapped onto triangle MNO. Now note, A goes with M, B goes with N, and C goes with O. So those are corresponding vertices. This line right here means is mapped to, so we know that ABC and MNO, these two triangles are linked. And if it's a reflection, these two triangles are congruent. Because this is a congruence transformation, I know that these two triangles are congruent. I know that triangle ABC has to be congruent to triangle MNO. Now, if I know that these two triangles are congruent, I know that all the angles are congruent, and I also know that all the sides are congruent. So I'm just going to write down what those congruent angles are. I'm going to say that A has to be congruent to M. B has to be congruent to N. C has to be congruent to O. And so I write that down here. Angle A is congruent to angle M. Angle B is congruent to angle N. And angle C is congruent to angle O. Now, I'm going to expand this up a little bit bigger so you can actually see it. And look, I'm doing the exact same thing. However, instead of writing it with just one letter here, I am using three letters right here. So angle A and angle BAC are the same angle. Angle M and angle NMO, the same angle. This and this are the same angle. This and this are the same angle. This and this are the same angle. And yes, this and this are the same angle. Notice, wherever you see a B, on the other side of the congruent sign, you're going to see an N. Wherever you see an A, you're going to see an M. And wherever you see a C, you're going to see an O. That's because these are corresponding vertices. They have to appear in that same order. So the vertex that matches with B is N. So if B is first, N is first. So look down here. So if B is second, what do you think second over here? N. It has to be. And so A right here is in the middle, and M is in the middle. These are your corresponding vertices. But down here, A is at the first position. So what do you think has to be in the first position here? Of course, it has to be an M. Now, I just noted the vertices of all this. So A is the vertex, M is the vertex, B here, N here, C here, O here. Whenever you have an angle, the middle letter is always going to be your vertex. Always. Always going to be your vertex. So let's go over to the congruent sides. So we're going to take this congruent statement right here, and now we're going to write down the congruent sides. I know that AB has to be congruent to MN. So look right here. AB, MN. A is first, M is first, B is second, N is second. So I have AB and MN are congruent. Notice that I wrote that they were line segments. So I put that little line segment symbol above the AB and above the MN. You know that segment BC has to be congruent to segment NO. How did I know that? These are your last two letters. These are your last two letters. So they have to match up because they're corresponding vertices. So look at this. BC and NO are congruent. Now we have to get that third side of the triangle in. And notice we're going to have to follow that same system. So if I did the first two, the last two, I'm going to pick up the last and the first and the last and the first. So C and A, CA goes with OM. These are our last segments that are congruent. What we call this is corresponding sides. AB and MN are corresponding, BC and NO are corresponding, CA and OM are corresponding sides. Remember, another name for corresponding is this whole concept of matching. They match, they're identical, they're congruent, okay? Here we have our corresponding angles, and here we have our corresponding sides. And because this is a congruence transformation, these angles are congruent, these sides are congruent. Now, if this was a dilation, that would not be true because a dilation is not a congruence transformation, it's a similarity transformation. The only time this is going to be true is if you have a congruence transformation. That would be a translation or a slide, a reflection or a flip, or a rotation or a turn. So translation, reflection, rotation, or slide, flip, turn. Now, I need for you to remember this. There are three very common lines of reflection. Three very common. One is the x-axis, one is the y-axis, and one is a line called y equals x. You have to remember this. So you have to remember the very common lines of reflection. X-axis right here, y-axis right here, and the line y equals x. So let's look at something that's reflected on the x-axis. So I have a pre-image up here, and all I did was draw a line segment. That's all I did. And I want to reflect this line segment on the x-axis, which is here. It's that horizontal line. Another way of saying the horizontal line or the x-axis would be y equals 0. That's going to be our line of reflection or our line of symmetry. So what we're going to do is we're going to reflect this pre-image right here on the x-axis. So when I do that, I'm going to draw a line that goes from the vertex perpendicular to the line of reflection. Then I'm going to do the same for the other vertex right here. Now, I'm going to continue that line down. And then what I'm going to do is I'm going to measure how many units is this right here. Well, we can actually count it. It's 1, 2, this is 3 units. So if this is 3 units from the line of symmetry, this has to be 3 units as well. So I know that my reflected point for A is going to be 3 units on the other side of the line of reflection. So if this is 3, this has to be 3. So my point of reflection would be right here, M. Then notice, if this is 7, 3, what would this point be? Well, it's still the same x value, but we've gone 3 below the x-axis, which means it would be a negative 3. Now notice these two reflected points. Do you see that the x stays the same? So the 7 and the 7 are identical. But what happens to the 3 here? We change the sign, and that automatically gives you what that y coordinate of the point is going to be. So instead of it being a 3, it's going to be a negative 3. So take a look at this right here, okay? So using that same concept that we used for this right here, I'm going to bring that over and I'm going to say the x's should stay the same, and then the y's, the number would stay the same, but the sign changes. So instead of it being a positive 7, the reflected point on the x-axis would be a negative 7. So if we look at this, that's exactly what happens. This is 7 units long, so this has to be 7 units long, but it's below the x-axis, which brings us to the negative 7 for the y-coordinate. So whenever you reflect a figure, an image, a point on the x-axis, or y equals 0 is another name for this, what happens is the x coordinates stay the same, the y coordinates, the sign changes. The formula is right here. To reflect a point in the y-axis, multiply its y coordinate right here by a negative 1. So if they would have given us this, what we would have done, and they said reflected on the x-axis, this would have moved up and this would have moved up. And if we multiply a negative 3 times a negative 1, that gives us a positive 3. If I multiply a negative 7 times a negative 1, bingo, it brings us up here to positive 7. So notice how the formula works. If you're reflecting something in the x-axis, it is so easy. All you do is change the sign of that y coordinate, and you found the new location for the reflected point. Now, let's talk about reflection in the y-axis, okay? So the y-axis is this right here. You knew that already. So instead of us folding something horizontally, we're folding it vertically. So what I'm going to do is I want you to know the official name for the y-axis, and it is x equals 0. So this becomes our line of reflection or our line of symmetry. We're going to use the same concepts we talked about in the previous examples. So I'm going to take my pre-image, which is right here, okay? And let's look at this negative 2, positive 3. So this point right here is you go over 2, up 3. I want to reflect this on the y-axis. So what I do is I'm going to draw a perpendicular line from the point to the line of reflection. I'm going to draw a perpendicular line from the point to the line of reflection. I'm going to continue that line over, and what I'm going to do is I'm going to measure how big is this line segment here, because that's telling me how far I have to go on the opposite side of the line of symmetry or the line of reflection. So what happens is I can count it. It's 2 units. 1, 2. So how far do you think we're going to go over on this side? Of course, we have to go 2, because remember, this and this have to be congruent. They have to be congruent. So if this is 2 units, this is going to be 2 units. Now look what happens to the coordinates. Here we have a negative 2, positive 3. Here, right here, we go over 2 and up 3. This is a positive 2 and a positive 3. Notice the differences between these two coordinates. Can you see it? Sure you can. Notice the y coordinate stays the same, doesn't it? It didn't change. 3 here, 3 here, because you're going up 3 and you're going up 3 here. However, you're going back 2 from the y-axis, and if you go back 2 here, you have to go forward 2 here, which brings you to a positive 2. So if we take that same concept and we apply it to this point right here, -15, -4, what would be the reflected point on the y-axis, or the x equals 0 line? Based upon what we did up here, we know that the -4 is going to stay the same. However, the sign is going to change on the x coordinate. So instead of it being -15, -4, it's going to change. It's going to be a +15, -4. At least I think it is. Let's check. Look at this. 15, -4, -15, 4. This is amazing. I could have done the same thing that we did in the previous examples. I could have drawn a perpendicular line from the vertex to the line of symmetry. I could have measured that, and it would have been 15 units long. I could have then gone a perpendicular distance from the line of symmetry out here for 15 units and put a point, and it would have been the reflected point of A. So A and M are mirror images of each other when reflecting on the y-axis, or the x equals 0 line. Okay? Now, the formula that we use for this is right here. To reflect a point in the y-axis, here's what you do. You multiply its x-coordinate by a -1. So we're going to take that first number and we're going to multiply it by a -1 to get the reflected image in the y-axis. And this holds true for this and for this. Now, one of the favorite lines of reflection that they like to use in tests is this right here, y equals x. You have to be able to draw that in. You have to be able to recognize it, okay? So this is the y-axis. This is the x-axis. And if you cut the first and the third quadrants in half, you're going to get this line right here, which is y equals x. I want you to look at this and I want you to memorize it. You have to know this. Yes, you have to know this. It's not on the formula sheet. You have to memorize it. You have to know that this is the line y equals x. Okay? Now that you know that, we're going to do the same process that we did in the previous examples. Here's my pre-image right here. It's a line segment. I have A at -9, 4, and I have B at 4, 6. I want to reflect it on this line right here, y equals x. So you know what we have to do. We have to draw a perpendicular line from the vertex down to the line of reflection, or the line of symmetry, right here. We're going to measure this, and then we're going to draw another perpendicular line directly on the opposite side, the exact same distance, and that's going to give us the reflected point on the other side. Draw the perpendicular line. We know this has to be 90 degrees. Measure it. So you're going to take your ruler and you're actually going to measure the line. Then you're going to go from the line of reflection out in the other direction It's going to be a perpendicular line segment as well. Has to be. You're going to go that entire distance. The measure of this and this are the same. And this is going to be your point of reflection for A. So A is reflected by M, and M is reflected by A. So how do we find this point right here, the reflected point for here, the same way? I am going to take and draw a perpendicular line from the vertex to the line of reflection. I'm going to measure it to make sure that this equals 90 degrees. Grab my protractor, make sure that this is a 90-degree angle. Has to be perpendicular. Perpendicular, the upside down T. I'm going to measure this distance, then I'm going to go out with another perpendicular line segment, the exact same distance as what I just measured, and then I'm going to draw another dot. This point and this point are now mirror images of each other. B is the reflected point of N, and N is the reflected point of B. Now, take a gander at this, okay? If you look at B and you look at N, look what happens. Do you see a relationship between the numbers of the coordinates for B and N? Take a look at it. What do you see? If you're looking at it, you'll notice that to get from B to N, the Y becomes the X, and the X becomes the Y. So the ordered pair just flips when you are reflecting something on the Y equals X line. It flips. If we were given N, we would know that the reflected point on Y equals X would be 4, 6. Look, it is. Bingo, right here. So let's go down here. I want to reflect A, which is at negative 9, 4, on the line segment Y equals X. Can you immediately tell me what that point would be? What would it be? Do you have it? How did you get it? And how did you get it so quickly? Well, just thinking about it, I'm going, okay, so I think the points, we'll call it M. And okay, the formula tells me I'm going to flip flop the numbers. So instead of 4 being second, I'm going to put it first. And instead of negative 9 being first, I'm going to make it second. So my reflected point should be 4, negative 9. Would you agree? 4, negative 9. Let's check. So I'm going to come over here and I'm going to go over 4, down, negative 9. Bingo. Look, exactly the reflected point. So when you're reflecting a point on the line Y equals X, what happens is all you're doing is just interchanging the X and the Y coordinates. The formula for this looks like this, okay? To reflect a point in the line Y equals X, you interchange, which means you flip-flop the X coordinate and the Y coordinate. So instead of it being XY, it becomes YX. And there you have it. How you reflect a point in the line Y equals X. Now, right here, you see a handy dandy chart that I found that I thought was just really simple. And it basically gives you the concept of reflection. Okay. So here we're reflecting on the X axis. Notice that X The x-axis is red. Here we're reflecting on the y-axis. The y-axis is red. And here's our friend, our buddy, y equals x. So we know what happens is if we're reflecting on the x-axis, the y changes signs. Here's the formula. If we're reflecting on the y-axis, the x's change signs. Here's your formula. If we are looking at y equals x, what happens is x and y's flip-flop. And so what we get is xy equals yx, or is mapped to yx. And there we have it. Here is a handy-dandy chart for reflection in the coordinate plane. Now let's work on a problem together, okay? So the instructions read, graph triangle ABC, where A is negative 5, 8, B is negative 1, 5, and C is negative 4. And what they want us to do is they want us to reflect this triangle ABC on the line y equals 3, okay? So what we're going to do is reflect this triangle on this line. So you have to know where this line is right here. That's huge. And so if you don't know where this line is, you're not going to be able to do the reflection. So you have to be able to graph that line, y equals 3. So let's graph the line. So you know that it doesn't matter what the x value is, y is always going to be 3. So if we look at this, y equals 3 is a horizontal line at y equals 3. So here is y equals 3. That's our line of symmetry. That's our line of reflection. So we're going to graph triangle ABC. We're going to graph our pre-image right here. This is our pre-image. We're going to graph that guy. So I graph my A, B, and C, and I connect them. All right? Now, you know what to do. We're going to draw a perpendicular line from A to the line of reflection, from C to the line of reflection, and B to the line of reflection. We're actually going to measure it to see how big it is, and then we're going to draw another line on the opposite side of the line of reflection, the exact same length. So here, when I draw my perpendicular line, I know that this is 1, 2, 3, 4, 5. This is 5 units tall. So I'm going to have to go on the other side 5 units down. This is my new A prime right here. And so it would be negative 5, negative 2. I'm going to look at my B. I'm going to draw a perpendicular line from B to the line of reflection. When I do that, I'm going to then measure how big is that line segment I just drew. Well, it is 2 units big. So how far below the line of reflection are we going to have to go to find our reflected point? Yeah, 2. 1, 2. And so our B prime is going to be right here, 2 units below the line of reflection. So here's B prime. And we know the coordinate is negative 1, positive 1. Okay? Now we have to do C. Now look, C is on the opposite side of the line of reflection. See, these 2 points are above the line of reflection, and this point is below. So what are we going to do? Well, instead of drawing the line down, we're going to draw it up. Because remember, we're drawing the line from the vertex to the line of symmetry, or the line of reflection. So when I do that, I count how big it is. 1, 2, 3. So this is 3 units from C to the line of reflection. So to get to C prime, I'm going to go 3 units on the opposite side. 1, 2, 3, and that's going to bring me right up here. So notice, the two triangles sort of are intertwined with each other. They're sort of inside one another, and that's okay. That's because the line of reflection cuts through the pre-image. So those two triangles are going to be mixed together. So now I'm going to connect the points, A prime to B prime, B prime to C prime, and C prime back to A prime. And this is our reflected triangle. Pretty cool, huh? Pretty cool. I'm going to zoom out so you can see. And usually they will ask you for the vertices of the image. So that's what I included right here. Right over here, triangle A prime, B prime, and C prime. Here's A prime, here's B prime, and here's C prime. Whew. Now it's your turn to take the lead. Let's see how you can apply everything that we've learned. The instructions read, graph triangle ABC, and here are the vertices for A, B, and C. And they want you to reflect this triangle in the line y equals x. Remember where y equals x is. If this is our coordinate plane, y equals x cuts right in between quadrant 1 and quadrant 3. This is the y equals x line. So you're going to reflect it on this line right here. Okay? Now, your reflected image is going to be triangle A prime, B prime, and C prime. When you give your answer, you are going to tell me the coordinates for A prime, B prime, and C prime. Remember to show your work in your notebook, and please box in your final answers. If you have any questions or issues, please ask for help. You may check your answers on the next slide. Now please pause the video and complete your work, and when you're finished, press play to continue. Here's the answer to the problem. Please pause the video and check your answer. When you're finished, press play to continue. This is it for today's video. We really did some great work. If something does not make sense to you, that is your cue to ask questions. In fact, it's your responsibility to ask questions if you do not understand something. Now, you can come to me, you can visit with one of your classmates or your shoulder partners, or you can even ask AI for a step-by-step explanation. Please remember that we're a team here, and we're all here to help one another succeed. You learn best by breaking complex concepts down into smaller, more manageable skills. And that's exactly what we did here today. You are turning your practice into your superpower. Now, you know I believe in you, and I know that you can do this. You are working your way to success, learning one skill at a time. I want you to have a great day, and thanks for working with me.